Hopefully, you came up with an assortment of risks for our newly developed SLOs in the activity at the end of the last lesson. We expect there will be a fair bit of overlap with the list we came up with, which you'll see later on in this video. But while creating the list is an interesting thought exercise, on its own, it isn't particularly helpful for answering the questions we posed earlier. What we really need is to prioritize our list of risks based on their expected impact to our SLO. We've created a spreadsheet for this purpose, and I'll be showing you how it works. But first, let's go over some of the theory behind it. To make the risks comparable, we need to find a common metric to quantify them, and for this common metric, we return to the error budget. In the last lesson, we introduced a definition of risk taken from safety engineering practice, the probability of an event happening multiplied by the likely impact of that event. These factors translate directly into an estimated time between failures and a period of downtime from each failure that burns some portion of the error budget. From these numbers, we can derive an estimate of the bad minutes of error budget we can expect with each risk to burn over the course of the year, a number that is directly comparable. We consider such a long time horizon for the error budget because many of the risks to distributed systems are rare but catastrophic. We might estimate that it will be 5 years or longer between events like the accidental deletion or corruption of a serving database. But if this does occur, it could well burn multiples of a monthly error budget. Comparing against a yearly budget helps smooth out the effects of these rare events. Estimating time between failures is relatively easy to understand, but we break the estimate of downtime out into 3 components: estimates of time to detection, time to resolution, and the percentage of users impacted. Thinking about each of these dimensions in isolation is helpful, and the resulting estimates are easier to both justify and reason about. Impact percentage is particularly useful for modeling things like a failure in 1 out of n availability zones, or only write requests failing, or a bad push to canary tasks that serves a small fraction of your production traffic. You can even set the number to be larger than 100% for modeling a failure that disproportionately affects your most important traffic. Think US retailers on Black Friday or Cyber Monday. Let's see a demonstration of this in action. On the screen, you'll see 2 links. The first is to the master version of CRE's risk analysis spreadsheet, which you can make a copy of when analyzing your own service. The second is a copy of that master sheet with risks and estimates for our example service. We filled in the risk catalog sheet of this document with a set of 9 broad risks. For each of these risks, we've estimated our time to detection, resolution and failure, and filled in an impact percentage. This can be more art than science at times. Remember that Fermi estimates are approximately correct in aggregate, even if individual values are off. Like bucketed latency thresholds and SLO targets, it's best to choose from a small set of easy-to-understand round numbers when estimating. For time to detection, we've used 5 minutes to mean detected quickly by monitoring, and 240 minutes, 4 hours, to mean detected by users. The outlier here is degraded write performance. We're assuming that it takes some time for slow requests to consume enough error budget that someone gets alerted. The story for recovery time is a bit more complicated. Generally, if the recovery time is estimated to be longer than an hour, you should round to the nearest hour or half hour. Stick to simple fractions for partial impact as much as possible, though this is one of the most useful things to tweak. Finally, for time to failure, round up. Once you're past a week between failures, only estimate in multiples of a week. Same for months, quarters, and years. We hope that most of the risks and estimates we've put down are self-explanatory and plausible, but there's one that might be surprising. Modeling an expected minor increase in errors due to a new software release being rolled out stretches our terminology. We have 0 time to detection because we expect the increase to occur. The time to recovery models the length of time it takes to update all web servers with the new software, and the time to failure models the time between releases. Since we push 4 times a week over the course of a year with gaps for holiday periods, that's approximately a push every other day. The spreadsheet also allows you to define common factors that apply to all occurrences of each risk in the risk factor sheet. For example, this can be really useful for modeling the effect of operational overload as a constant increase in time to detection. We've not used it in this demonstration. It doesn't play well with the way we've modeled our daily release cycle, because each release is considered to be a separate incident. This particular case is not an operational response to a risk, which these factors would apply to, but a known system behavior that burns error budget. Remember those risks we asked you to brainstorm at the end of the last lesson? If you've not already done so while watching this lesson, please put them into your own copy of the risk analysis spreadsheet and estimate their error budget costs.